Let's work through an example of alcohol dehydration. I recommend that as you learn more and more organic reactions, one important thing is to try to keep things in context as much as possible. So give a 1 or 2 sentence description of what the alcohol dehydration reaction does, all right? And just like when you learn to define words, you don't want to use the words in the definition. So for instance, you wouldn't want to say alcohol dehydration is the reaction that dehydrates alcohols. Okay, you want to be a little bit more descriptive than that, maybe in terms of the products that are formed or something of that nature. Well, an alcohol dehydration, you lose the elements of water from an alcohol, so I guess I have to use alcohol in the definition. You lose the elements of water, and the product is a what? The product is an alkene. Okay, so if you know up front what type of product you're going to get in terms of important functional group within that product, you're kind of halfway there already before you even start to deal with the particulars of the reaction. You might be able to make a pretty good guess in terms of what the product would be. Okay, so here is a compound. You might even be doing a dehydration of this molecule in the lab. All right, so this is 2-methyl cyclohexanol. All right, so here's the 6-membered ring. That's the cyclohexane part. It's an alcohol, so an alcohol has an OH group attached. And so the way that this is numbered is the alcohol carbon has number 1, and then we would number this way so as to give the methyl-bearing carbon the number 2, and so on. Okay? So just one question about 2-methyl cyclohexanol. Tell me about the possibility of stereoisomers of this compound. How many different stereoisomers are there of 2-methyl cyclohexanol? There are 2 stereogenic carbons. There's one here, and there's one here. So you would expect how many possible stereoisomers? There's no obvious plane of symmetry or anything to any of the isomers in this case. So there would be 4 total stereoisomers. You could have the cis compound where the methyl and the OH were on the same face. You could have the trans compound where the methyl and the OH are on opposite faces. And then for each the cis and the trans, you have 2 possible enantiomers. So I won't do it here, but you might, just for practice and review of stereochemistry, you might go and try to draw all 4 of those. Okay? In this particular case, and I think if you do this experiment in the lab, you actually buy from Sigma Aldrich. It's a mixture of cis and trans isomers. So I'm not specifying the stereochemistry here. So another thing to know about each type of new reaction that you learn are what are the typical reaction conditions. So what are the typical reagents or other conditions that you would see above and below the arrow, the reaction arrow, because sometimes if you can just identify those, then that will also tip you off, hey, I have an alcohol as a starting material. I have these special reagents that I know are associated with alcohol dehydration. You want to find as many ways, complementary ways as you can of being able to identify a particular type of reaction. So in this case, the reagent is phosphoric acid. So I will write phosphoric acid out in great detail here, but please be aware that you may well just see H3PO4, and you should be able to draw the corresponding Lewis structure. And then the other thing is that often these reactions are done in concentrated phosphoric acid. 85% phosphoric acid is concentrated phosphoric acid. The other 15% is water. But you can think of this as a concentrated acid solution. And after all, if you're trying to dehydrate something, you should have as low a concentration of water as you can, because dehydration involves removal of water, and doing the reaction under a lot of water, that's not a very good way to do it. And then oftentimes these reactions will be heated up. So if you see this type of reaction conditions and an alcohol to begin with, you should immediately say to yourself, this is an alcohol dehydration. The product will be an alkene. So can you please write down the product or products of dehydration of 2-methyl cyclohexanol? How can I do this? I could work through the entire mechanism, and maybe we'll do that in just a bit. But another way to think about this is to identify the, let's call it the alpha carbon, the carbon to which the OH is attached. So there's the alpha position. So if we're going to lose the elements of H2O, here is part of H2O. There's going to be an H that we're going to lose. And this is a type of elimination reaction. And so where would you expect the H possibly to be lost from? Is it going to be lost from the alpha carbon? No, it is not. It is going to be lost from a position adjacent to the alpha carbon. So we have to look for the beta carbon or carbons. In this case, there are 2 of them. One of them is here, and one of them is here. So that's carbon 6 and carbon 2. Are these 2 beta positions equivalent? In other words, would we get the same product if I did loss of the H from carbon 6 versus loss of the H from carbon 2? No, they're very different, right? This carbon has a methyl group on it. This carbon does not. So let me just call this beta, and I'll call this beta prime. So here's another way to think about alcohol dehydration reactions. You're going to lose the OH group, and you're going to form an alkene product. And the alkene, the double bond, is going to connect the alpha carbon to the beta carbon. And if there's more than one beta carbon, then you're going to have more than one possible product. So with that in mind, and without worrying too much about the mechanism, can you draw 2 reasonable products for this elimination reaction? Well, in one possible product, the carbon-carbon double bond would be between carbon 1 and carbon 2. So to make this product, we would have lost the hydrogen from carbon 2. And then another possible product would involve loss of one of the hydrogens from carbon 6. So maybe we would expect to get this product as well. Okay? So if you came up with those 2 products, you're in good shape so far. What I would like you to tell me next is, what is the relationship between these 2 products? What are they to each other? They have the same molecular formula, but they're not identical. They actually have different atomic connectivity. Here there's a double bond between carbon 1 and carbon 2, whereas here there's a single bond between 1 and 2 and a double bond between 1 and 6. So these are structural isomers. And then the other thing that we can call these, they are structural isomers that share a common history, if you will. They were both generated from the same starting material through the same reaction, in a reaction that either went this way or went that way. And we'll look at the mechanism in a little bit more detail in a second. But these types of structural isomers that are formed from a single starting material through a set of related reactions, these are known as regioisomers. So regioisomers are a subcategory of structural isomers. Okay? And so that's what we could call these. That's probably the best way to describe the relationship between these two structures. The next thing I would like you to do is focus on the carbon-carbon double bond of each of these alkene products and fill in any hydrogens directly attached to the sp2 hybridized double bond carbons that are not explicitly shown in the structures as I drew. Fill in the missing hydrogens, if there are any, on the sp2 hybridized carbons. Well, this carbon number 2 already has 4 bonds, so that's fine. We don't need to put any more hydrogens on there. This carbon, however, has 1 hydrogen remaining. So if you go back to carbon 1 here, there was 1 hydrogen there, and it's still there in the product. And then in this product right here, there's 1 hydrogen left at carbon 1. There's 1 hydrogen left at carbon 6. Carbon 6 had 2 hydrogens to begin with. To make a double bond here, we lost 1 of them along with OH. So there are the products with all the hydrogens shown on the double bond. So the next thing I want you to do is I want you to tell me for each of these alkenes, is the alkene a completely unsubstituted alkene? Is it monosubstituted? Is it disubstituted? Is it trisubstituted? Or is it tetrasubstituted? And remember what that means is you have to count up the number of non-hydrogen groups directly attached to the sp2 hybridized carbons of the double bond. Let's start with this structure right here. So here is one of the sp2 hybridized carbons. Here's the second one. Let's count up the number of non-hydrogen groups attached to this carbon. Here's one. This is certainly not a hydrogen. Here's a second one. Let's go to this carbon. Here's a third group. Don't worry that this and this are attached by this ring. It doesn't matter. We still count this as a non-hydrogen thing, and this as a non-hydrogen thing, and this as a non-hydrogen thing. But of course, this is a hydrogen. So what kind of double bond do we have here? This would be a tri-substituted double bond. How about this one? Well, this carbon has 1 non-hydrogen thing. The other one's hydrogen. This carbon has 1 non-hydrogen thing. This one's hydrogen. So this would be a di-substituted alkene. All right? So the next thing I need you to tell me is, according to Zaytsev's rule, which of these should be the major regioisomer of the product? Should we get more of the tri-substituted, or should we get more of the di-substituted, according to what Zaytsev has to say? Zaytsev's rule says that in an elimination reaction, you tend to get more of the more highly substituted product. So we would expect this to be the major product, according to Zaytsev's rule, and this would be the minor product. So one way of formulating Zaytsev's rule is when you have regioisomeric alkenes that can form, the predominant one will be the more highly substituted alkene. Let's go back and look at the starting compound. So another way of thinking about the Zaytsev's rule has to do with where you remove the proton from. So we could either remove the proton from here, or we could remove the proton from there. So can you think of the way Zaytsev would talk about where we should remove the proton from. Should we remove the proton from carbon 2, which has 1 hydrogen attached, or should we remove the proton from carbon 6, which has 2 hydrogens attached? So Zaytsev says, take the hydrogen from the beta carbon that starts out with the fewer number of hydrogens. So this is kind of the reverse Robin Hood philosophy. Instead of taking from that one which has more, you take from that one which has less. So again, if we took this one, we would make a double bond between 2 and 1. So Zaytsev says, take this one. So there are 2 equivalent ways of stating the Zaytsev rule. You can either think about it in terms of the product that you make. You predominantly make the more highly substituted alkene product, or you can think about it in terms of the starting compound. Take the proton from the beta hydrogen that has the fewer protons to begin with. And then finally, what I would like you to do is I would like you to write a mechanism for formation of these 2 products. So write a mechanism, and let's stipulate that the mechanism that you write should be an E1 type mechanism. All right, so pause the video and try to do that. Okay, so pause. In alcohol dehydration, we face this issue of having an OH group which is not a good leaving group, and so we need to improve the leaving group, and that is done through use of an acid. In this example, it is phosphoric acid. So you need to be sure you know how to write the Lewis structure of phosphoric acid. And then the first thing we're going to do is we're going to protonate the OH group. So a lot of the steps here are going to be readily reversible, maybe all of them, because you could put a proton onto your alcohol and generate its conjugate acid. And that's also going to generate the conjugate base of phosphoric acid. Okay, so this is hydrogen phosphate here, dihydrogen phosphate. And so here we have now a molecule with a good leaving group attached. Let's keep track of the alpha carbon, carbon 1, and the 2 potential beta carbons, carbon 2 and carbon 6. Remember, there's a hydrogen here, there's a hydrogen here, and there are 2 hydrogens there and there. So if you want to pause the video at any time and work through the rest of it yourself. We've now made this into a much better leaving group, so that leaving group can leave like that. So at this point, we have just a single hydrogen left at carbon 1, and that's a carbocation. We have a methyl group here, and then we have still 2 hydrogens there, 1 hydrogen there. So there's carbon 2, there's carbon 6. And so now if we think about the elimination fate of carbocations, maybe we're pretty close to where we need to be. We've also lost a molecule of water here. So we've lost water. If water adds back to this carbocation, we're going to go back where we started from. So a lot of times if you're trying to do a dehydration, this is a good opportunity to drive the reaction in the desired direction. If you could somehow remove the water, maybe by distillation, then you could successfully drive this in the dehydration direction. On the other hand, if you have an excess of water around, you may be in trouble if you're trying to dehydrate, because the thing would just revert back to starting material. And so now we're pretty much, pretty close to being done. We need a base. So the best base we have in the reaction mixture is the conjugate base of the acid that we started with. And now we could deprotonate either at this position. That would give us the tri-substituted alkene product. There it is. So here's carbon 1, and here's carbon 2. Or the base could remove a proton from the other position, and we could make the double bond between 6 and 1. And so that would account for the formation of the di-substituted product that has a bond, a double bond between carbon 1 and carbon 6. And then also notice that in either case, the acid is regenerated. So we can think of the acid molecule as a catalyst. It's required to do this reaction at a reasonable rate, but it's regenerated at the end of the reaction mixture, and it could go back through the cycle again. Okay? So here is an E1 type mechanism for dehydration. Make sure that you're able to work through that efficiently. And think also about the reverse process. Could you write a mechanism to go back the other way? So could you start from this alkene or this alkene and go back in the other direction to the alcohol? What kinds of conditions might be used to do that? And would you expect that? How would you expect that to work? But maybe that's best left for another day.